So we've heard about backprop and multi-layer nets. There's a special kind of network which is really central to dealing with sequences. You've all heard of recurrent networks. So I'm going to try to go a little bit deeper than the standard explanations today. The heart of what's going on with recurrent nets is in this equation, which is really, really simple. It's an old equation that dates back well before recurrent nets. It's just here a deterministic dynamical system with a state vector st, which is obtained through a parameterized function f theta of the previous state st minus 1 and the current input xt. And we're going to have a sequence of these x's. And so if you unfold the computation, as we say, you get the kind of graph that you see on the right, where we have a sequence of inputs and we have a sequence of states. So remember, each of these states, in the case of recurrent nets, is going to be a real valued vector. And the x's could be anything that you usually put an input to a neural net. The really important thing is that the same parameters are used over and over, right? So in a normal feed-forward net, you have different weights at different layers. Here, you can think of that as a very deep net where the same parameters are used for all the layers. And also you have the input coming in like at each layer, if you think of this as a deep net going to the right. The other interesting thing about this is to realize that what we're really doing is computing a variable size function, a function with a variable number of arguments. So if you look at the state at time t, it really is a function indexed by t of the first t inputs. And so now what we're building is a mechanism to map variable length sequences, and later we can see we can generalize to variable length data structures to fixed size vectors. Now those fixed size vectors could be pretty large. And you'll see, for example, when we talk about memory networks and things, sort of modern extensions of recurrent nets, the state could be so large that you can actually store everything about the past. But the original idea is that that state is a sort of a summary of everything we've seen before. But it's not necessarily a summary that is like in a compression that keeps all the information, but it's a sort of a smart summary that's going to be trained to keep only the information that we actually need for further processing. So this is a building block, but we're going to use that state to do things, to predict what's going to happen in the future, to take decisions, to do things like translating, generate speech, or whatever it is that we're doing with sequences. Okay, so that's the basic building block. And of course, we can write it compactly with this kind of a circuit diagram, which is inspired from electrical engineering, where we use a little black box to indicate a delay of one time step between the update of the state and the previous state. So if we stick on top of that some outputs, that's going to depend on the current state, then we get a graph like this, which can be used to map a sequence of inputs to a sequence of outputs of the same length. So these were the kinds of recurrent nets I was playing with when I was doing my PhD in the late 80s. And at that time, we didn't have the kind of modern things that I'll show you later, where we can do things like map sequences of some length to sequences of other lengths. But anyways, this is sort of the first kind of use that people have done, where you causally process a sequence to generate or to predict or to transform into another sequence. Now, there's something really, really important in many applications about recurrent nets, which is that we can use their output as an input for the next time step. And when we start thinking about this, we can use recurrent nets as what we call auto-associative generative models. So we can use recurrent nets to generate sequences, and we can use them to generate sequences in a probabilistic sense. We can represent a probability distribution over sequences of vectors, over sequences of symbols, over sequences of anything you want. So this is a really, really important advantage of recurrent nets, and sort of frames them in a classical maximum likelihood setting, which of course is very convenient. So let's look at this more carefully. If you have a sequence x1 to xt, and you're trying to characterize their joint probability, in other words, we're trying to characterize how the different elements of the sequence interact with each other in terms of their statistical dependencies, then we'd like to have some kind of model of the joint. But the joint distribution over a variable length sequence is a complicated object. There are many random variables, and it's not clear how we can write a function that has a variable number of inputs. But remember, with recurrent nets, we can deal with variable length data, and in particular, we can compute something like this joint probability. So we're going to use this trick that I showed you in the previous slides to represent the joint, and the way we're going to be doing it is we're going to decompose the joint as a product of conditionals. This is, coming out of simply the definition of conditional probability, right? So if P of A and B is just P of A given B times P of B, right? So if we apply this recursively and I do it for P of A, B, C, right, we get the product rule, and this is exactly what we have here. But replace A, B, C by x1, x2, x3, x4. Okay, so that means we can represent a joint distribution which otherwise would seem like a very daunting task because you have so many variables, so many interactions, into a series of conditional probabilities where on the left-hand side of each probability we have only one random variable. So capturing the joint within that random variable condition on the past is much easier than trying to capture the joint overall. So we've sort of broken down this very hard problem of modeling a joint distribution into modeling a bunch of conditionals, each of which is much easier to do. All right, so practically how does that relate to a recurrent net? Well, remember we have this sort of state update equation, and we're going to produce some outputs. But now let's think of those outputs as telling us about the probability distribution of the next xt given the previous ones. The previous ones are summarized by the state. So the state at t summarizes all the previous x's. And now we're going to compute, say, a probability. Let's say it's a symbol. So we're going to produce a probability for each of the possible symbols, values, for the next time step. And then we could sample from that distribution, and we get actually a new symbol, and we could stick it in as the next input. So that's how we're going to be generating a sequence, right? Once we are able to compute those probabilities, we can also sample from them, and we can use the sampled symbol for the next time step as an input to the next time step, and then we use that to feed the update of the next state, and then for the next state we can compute again the probability for the next symbol, we can sample that, and we just stick it in as the next input, and so on and so on. And this way we can generate a sequence. So we can do all the things that we usually care about with probabilistic models. We can sample, here it's a sequence. We can compute the probability of a given sequence. And because those probabilities are fairly smooth, easy to compute functions of the parameters, which are all the weights that go in the middle, we can compute the derivative of the log likelihood with respect to parameters, and so we can do maximum likelihood training. So how do we compute the probability of a sequence? Well, so if somebody gives us a sequence, now we're not going to be generating the symbols because we have them, but we can just compute by applying this formula. So we force those x's to be the observed values, and then we see what probabilities we're getting at each time step, and we take the probabilities for the observed thing, right, the actual next symbol in the data, and we just multiply those probabilities together. That's it. And once we can compute those, we can of course compute derivatives. We stick that in a automatic differentiation thing like Theano and TensorFlow and so on. All right. Any question up to this? These are really the basics, but it's really important to understand them. Yes?
Were there data sets in the early days that were motivating this?
So the question is about early days. As I said, I was working on things like this in the late 80s, and the main application I was looking at was speech recognition. There were already some people trying to use this for financial applications, time series data. I remember people working on other kinds of natural time series, like the sun's 11-year cycle and things like that. Yeah, I think the main application was handwriting and speech in those days, which were already using these kinds of recurrent nets. Yes?
because you are going so to the core of this, there is two questions.
Yeah.
I noticed in the previous graph that this looks like a final state machine.
Right.
Stochastic state machine. So I wonder if this is something that this is like a one right view to make sense of the literature.
So the question is this a finite state machine? No, it's an infinite state machine because the state is real valued. Yes. But it's of course very closely connected. Yes.
Yes. And then the second question is that you are saying that you are getting a compact representation of the probabilistic distribution of sequences.
Yes.
Then I wonder about connection with Bayesian nets work together as they're trying to do this.
Okay, so what's the connection to Bayesian nets? So it's a good question. You can actually think of this picture like a graphical model where the nodes for the state are particular in the sense that they're deterministic nodes. So you can have deterministic nodes in a graphical model. And in that sense, this looks like the same graphical model as things like hidden Markov models, except that the state is continuous valued and high dimensional compared to HMMs, and much richer because of that. And the other big difference is that these states are now have a conditional distribution given the past, which is deterministic, which means that inference when you go from left to right, in other words, if I know some inputs, I can compute the probabilities of all the future ones, is trivial. But inference going in the other direction, in general, is going to be hard. So it is a particular kind of directed graphical model. The other thing compared to other graphical models is that if you were to try to model the full joint, in general, it would be very, very expensive. And because we're using this sort of funny parametrization with this recursive use of the parameters at each time step, we're able to very compactly represent a joint distribution which would otherwise potentially require an exponentially large number of parameters if you look at the length of the sequence. So this is an interesting sort of particularly efficient way of representing a joint distribution. Okay, now we can play all kinds of games. Once we understand this principle, and there's a lot more that's not covered on that slide. For example, well, there are easy things we can do, like we can read a sequence and then predict or calculate some vector, right, which we can use for classification or whatever you want. So that's sort of a trivial thing. We can look at the final state after we read a sequence and then use it as input to some MLP or whatever to compute something we care about. So that we can do sequence to vector. We can do sequence to sequence of the same length. That's what I showed in the previous slide. We can do vector to sequence. So as I said earlier, we can generate a sequence, but it's very easy once you have a generative model to make it a conditional generative model with neural nets. We just stick in extra inputs. So we had our recurrent net that could generate a sequence of outputs, but now we take some vector of features that we want to condition that probability distribution over sequences, and we just use that as an extra input that's going to condition every state or every parameter, whatever parameterizations we care. So we can condition on a vector, and of course, once you start thinking a little bit more about it, we can condition on a sequence. So that's a fairly new idea that dates back to around 2014 when we were trying to do machine translation. And so now think of it like, the way we thought about it is we have two recurrent nets, and we call this model the encoder-decoder recurrent nets, and the Google guys called it the sequence-to-sequence model, and I guess their choice of phrase stuck. But anyways, you take a sequence and you read it, so that's the same thing that I was telling you about before. Now you have a state that summarizes everything you've read in that sequence. Now you got a second recurrent net, could be the same one actually, you're just going to condition it differently. And now that one is a generative recurrent net, so it also has outputs, and its outputs are used as input for the next time step when you sample or when you clamp the inputs. It's just computing the conditional probability of that sequence given the input sequence. So now you have two sequences, an input sequence and an output sequence. What we're doing is we're reading the input sequence, sort of compressing it into a fixed size vector, and then using that to condition the generation of a next sequence, which could be a totally different kind of sequence. So that, that made a lot of sense for machine translation. But we're using this kind of model also to do things like in dialogue, where you read some context and then you generate an answer. So there are many situations where we want to read some sequence and then generate some other things conditioned on that. So that's the sort of the sequence-to-sequence model. Now, I mentioned that, but I would like to come back to this, that there are these two ways of using a recurrent net, a generative recurrent net, right? One is the way that we're actually running things when we train. When we are given a sequence, we call that teacher forcing. We force the sequence to be the one in the data, and we just compute the probability for those elements given the previous ones. And so what we see here in this picture is the y's could be given from outside. So the data here is x, y pairs, and the y's could be given from outside and then used as conditioning input to predict the next probability for the next y. That's what we do when we compute probabilities, and this is what we do when we compute gradients of the likelihood, because we are given some training sequence and we want to know what their probability is so that we can maximize that probability, compute the derivative with respect to parameters. But when we're going to be using the recurrent net to generate new sequences, we're going to be using actually a very different schema where the y's are not going to be given by the outside world. They're going to be sampled from the model itself. So now we have a sort of closed loop versus open loop process. These are two different kinds of dynamics. And if they're too far from each other, we're going to potentially be in trouble. And there's going to be a mismatch between the kinds of things that the network sees, the kind of context that it sees during training, and the kinds of context that it sees when it's actually running, free running, generating those contexts itself. Some similar issues arise in reinforcement learning. That's for next week. But this kind of mismatch can be a problem. So I remember when we were starting our work on speech synthesis with recurrent nets, that the network they wouldn't work very well initially. And although when you train them, they would see speech-like things, when they were generating, very quickly they went into some kind of configuration which didn't look at all like speech. And then they would sort of go off to crazy land and generate a big bang or go to zero or something like this. So because the recurrent net during training has only seen nice things like speech-like context, when you show it something very different, there's no guarantee that it does the right thing. And then if it was only one time step when this happened, the problem is that it feeds on itself. So you've got a kind of compounding of errors from time step to time step, and then it can go in crazy land and do very bad things. So this is a concern in some applications. And several approaches have been proposed to deal with that, which are connected to earlier work in structured output and reinforcement learning, like CERN and Dagger. So this is actually, I'm referring here to a paper by my brother Sami at Google and his collaborators at NIPS 2015, where they try to deal with this by injecting noise during training, so that instead of using the actual symbols that are in the training data, they randomly flip some coins so that sometimes, they inject a bit of noise in the input. So sometimes they actually use the symbol from the data, and sometimes they put in something random. Or some combination, and you can try to anneal that noise and all kinds of tricks, and there's some interesting questions about whether this is a proper way of estimating distributions. There are all kind of interesting questions around this, but I'm not going to answer them today. This, yeah?
Would it make sense to try and reduce this train-generate mismatch to correctly train on small sequences and then increase their size during training?
Yeah, this is called curriculum learning, and it could help. I don't think it completely solves the problem, though, because the problem is this running off into configurations that it has never seen. So you need to, so my mental picture of this is the way that we really fix this is you think of the dynamics, and you'd like to carve the dynamics so that when you are away from kind of dynamics of the data, the state-to-state transition brings you back towards things that are like the data. And one type of approach that I really like is based on GANs that you'll probably hear about later this week, generative adversarial networks, where we had a paper last year called Professor Forcing, where but there's now several ideas floating of that nature, where you try to look at the two dynamics and you try to make sure that one is going to be pushed towards looking like the other. But yeah, I think it's pretty much still an open problem how to solve this properly. Now in practice, the good news, and this was true in the example I gave of speech synthesis, the good news is that if you train sufficiently, eventually, even with maximum likelihood, these kinds of problems tend to go away. So really well-trained model, maximum likelihood will reduce probability mass away from the data and eventually get rid of those spurious modes, so regions where the model would like to put probability mass, but it shouldn't. And so in some cases, you don't need to do anything special, but this trick of injecting noise, I think is a good one to keep in mind as well. There was another question, or yes?
Why actually a simple plain RNN doesn't work so good? Instead of like there's vanishing exploding gradient.
I'll talk about the vanishing gradient problem.
Yeah, but only because of this, or there are other reasons why it's not?
I'll talk more about it. It's an optimization issue, yeah. So now we're going to start talking more about all kinds of architectural variants. So one kind of variation is to put in depth, right? That was of course the hot topic and is still, but maybe a few years ago people were exploring how can we, have deeper X and deeper Y, and how do we can have deeper recurrent nets? And actually there are many ways you can make them deeper, because if you look at the vanilla architecture, which is unfolded like this, where you have X to H and then H to the next H and to Y, each of these arrows is really like a one layer MLP in the standard vanilla networks. But we can replace each of these arrows by deeper models. Like we can stick in some extra hidden units between in the state-to-state input and state-to-state transition, or between the state-to-output transition. Model. So that's one simple thing. The other way we can make them deeper is we can think of the state as having multiple groups of units corresponding to multiple levels. And that really corresponds to a sort of constraint on the architecture. It's still like a recurrent net, but instead of think of this one big vector, and this is the next big vector, instead of having an all-to-all connection where all of the units here talk to all of the units everywhere, these guys only talk to those guys, and these guys only talk to those guys, but now we're going to have these extra sort of feed-forward links going from the input to higher levels. And if we now maybe think of these different layers in the neural net as a kind of hierarchy, just like in regular deep nets. So that's another way that's being explored that seems to work well. Now, once you understood this notion of dealing with variable-sized structures like sequences, it's very easy to extend this to other data structures. And the first of those that was studied in the 90s actually is tree structures. So instead of recursing once, we can have a two-level recursion. Two input recursion. So we can imagine a state here which depends on two states rather than just one previous state. It could depend on two states. Now the unfolded graph is a tree. So that's one nice trick. Another example of this is a special kind of graph which is not a tree, where you have at each node you have a grid, and at each node of the grid, the ij node depends on, say, the neighbor to the left and the neighbor to the north as inputs. And then you can also have different layers of this. So this is called multi-dimensional recurrent nets. Another kind of architecture which is very, very popular these days and highly successful, for example, we use it always for machine translation and other sequence processing applications, is the bidirectional recurrent net. Because one issue with the standard recurrent net architecture is that it has this sort of asymmetry in time, right? We go from the past to the future. And when you're processing things in a causal way, like you have to answer on the fly based on the data from the past, it makes a lot of sense. But when you're given a whole sequence, well, you could process the sequence left to right, right to left, or in many other ways. So why not do it, right? So that's it. You're going to have two recurrent nets, one that reads the sequence from left to right, one that reads the sequence from right to left, and then we're going to use their state as input to higher-level processing. So now at each time step, what do I have? I have two parts of the state. One part which summarizes the past, and one part. Oh, I guess I'm supposed to be somewhere else. And one part which summarizes the future. So really, what we're doing here is, instead of having, say, looking at each input, say input word, we now have the word interpreted in the context of everything before and everything after. And that's a really useful quantity to process. Okay, other kinds of games that can be played, instead of having the usual sort of vanilla neural net architecture like this, where you have an affine transformation of the input of the previous state, we can have multiplicative interactions between the input side and the previous state side. So and then you can have other variations on that. So this actually increases the expressive power of recurrent nets without requiring deeper computation. Because actually, one thing I didn't mention is that when you do this kind of thing, where now the state-to-state transition, now you can have interactions, nonlinear interactions between the previous state and the current input going into the next state. But the price for this is that if you look at the unfolded graph over time, the number of sort of nonlinearities that you have to traverse has just doubled. And as we'll see, because of this vanishing and exploding gradient problem, it can make training more difficult. And that is why when we wrote this paper, actually, we introduced skip connections, like these connections and these connections, which make sure that there are shorter paths that through which the gradient can flow more easily. Okay, so now let's talk about vanishing and exploding gradients. So I wrote this paper in 1992 and it was published in 94 called Learning Long-Term Dependencies with Gradient Descent is Difficult with Patrice Simard and Paolo Frasconi. And I was at Bell Labs in those days. I actually started this during my thesis and in my postdoc at MIT in 91, 92. I was trying to use recurrent nets for processing sequences, and I realized that when the sequences got longer, it was harder to train them to capture the thing. So I tried to simplify the problem, and I got to a very simple problem, which was just try to memorize one bit. So I have an input sequence which has the first symbol being either high or low, and then the rest is noise. And at the end of the sequence, the network has to answer a question. Was the first input high or low? Sounds like a trivial thing, right? It just needs to remember one bit of information. And in fact, we know that there's a solution with a single hidden layer, with a single weight, recurrent weight, that can store that information, and we can know what the optimal solution is for this. But when we try to train with gradient descent, with backprop, as the length of the sequences increases, the probability of training being successful decreased drastically. So we tried to understand that. And we came to the following conclusion. That if we want the network to store information reliably, especially in the presence of noise like in this experiment, then the dynamics of the network need to be contractive. So what does it mean that it be contractive? So contractive dynamics are such that 2 points mapped up by this, 2 nearby points are mapped to 2 even closer points. So that's what contractive means. And contractive means that there will be attractors, in the sense that if I were to run the same dynamics, like I would eventually converge to some attractors, which could be a point attractor, like a fixed point, or it could be a whole region. and we can characterize those regions where the dynamics are attractive, and we call them basins of attraction. So depending on where you start, like in my example, I could start with the high value or the low value, you would end up either in this basin of attraction or this basin of attraction. So in other words, the state being on that side means we store the value 0. Being on that side means we store the value 1. That's like a very prototypical simple thing. Of course, in general, you can have many more bits, but understanding even the 1-bit case is really interesting. And there's going to be this boundary in the state space where if you start on one side, you get into this basin, and if you start on that side, you get into this basin. And there are regions around those basins which are unstable. So what it means is that if you start here and you add a bit of noise, you may close to the other side. So there's sort of a sensitivity to noise because of the fact that it's not contractive in this middle region. So it turns out that whether the dynamics are contractive or not can be characterized very simply by the spectral radius, which is the largest eigenvalue of the matrix of derivatives, the Jacobian of the state-to-state transition. So if you look at the state-to-state transition, which is a function, and that function has a matrix, the Jacobian matrix of derivatives, d sti d st minus 1j, so at each ij element, and that matrix has eigenvalues, which in general will be complex, but you can look at their magnitude, and if the largest eigenvalue is less than 1, then the whole thing is contractive. And if it's greater than 1, then it can yield to unstable diverging trajectory. So it's illustrated by the size of these balls getting larger and larger. So a small ball could expand into a larger one, into a larger ball. In other words, if I start anywhere from the small ball here, I get to a larger one, and then anywhere from here I can get, one of those points here gets to one of those points there. So the size increases, and especially true if I'm adding noise at each time step. But if I'm in the sort of stable region, then I'm guaranteed to stay within that basin of attraction. Anyways, so those eigenvalues being greater than 1 or less than 1 are really important, and you can understand really what is going on with this vanishing gradient problem by thinking about these eigenvalues, the spectral radius. And the reason why this becomes important, if you think about the derivatives of the loss with respect to the state at some early time, it's just a product of these Jacobian matrices that I was telling you about. So by the chain rule, that's going to be the derivative of the final loss with respect to the final state times the derivative of the final state with respect to the previous state, and so on until we get to the last Jacobian ending at st. So each of these, except the last one here, is a matrix, the size of the state squared, and think of these matrices as numbers, right? So a single scalar number, if we multiply a bunch of numbers together, what's going to happen as the length of the sequence increases? Well, if those numbers are less than 1, we're going to converge to 0 exponentially fast. If those numbers are greater than 1, we're going to explode. And if you have a mixture of numbers that could be sometimes greater and sometimes less than 1, well, it's a little bit more complicated, but you can think now in random terms what's going to happen with the variance of those products, and the variance is also going to explode. So in some conditions, if the individual numbers have some particular properties. So this was actually this idea that when we multiply all the Jacobians, we could have vanishing gradients, was actually something that Sepp Hochreiter had discovered in his master's thesis, which was written in German, so I wasn't aware of it. I was working on the same thing at the same time, but he put it in his thesis, and actually it's because of this that he worked on the LSTM, which we now use. In fact, the idea of the LSTM was in his thesis in 1991. It only got to be, ironed out in 1997 was the first publication, but really It came from his work in 1991. So why is it a problem that we have this this product of Jacobians which could either become really large or really small? Well, to see the problem in its full glory, we have to look at the gradient of the loss with respect to the parameters. So there are many ways to decompose the gradient, but I'm going to use that way to illustrate what happens. So the gradient of the loss at some time step t with respect to the weights of a recurrent net, you can rewrite by the chain rule as dc t dA. So A now is the state, sorry for the change of letters. And that's for any earlier time, sum over all the previous time steps. In other words, how the state at time tau influences the final loss and how the weights immediately influence the state at time tau. And now this first factor we can decompose into dct dAt times dAt dA tau. And that's a Jacobian matrix, but that's the one which is equal to the product of Jacobian matrices. And that's, the number of these matrices is going to grow potentially such that that product will converge to either something very small or something very large. And that's a problem because it means the gradients will become either very large or very small. But there's something more subtle here, and this was the main point of the 94 paper, which is that in the conditions where we have stability, in other words, where we can store bits of information reliably, that's when the spectral radius is less than 1. And that's when that product of matrices is going to converge to something small. And then what's going to be the consequence? The consequence is that the total gradient is going to be a sum of terms corresponding to the effects of the parameters on the final loss associated to different temporal dependencies. So, when tau is just t minus 1 is the effect of the previous time step on the next time step. And when tau is 1, it's the effect of the beginning of the sequence on the final time step t. So the sum here is over different temporal dependencies, different spans, where we're looking at the dependency in the sequence from here to here, or from here to here, or from here to here, right? And what this says is that the terms corresponding to things far in the past will be exponentially smaller if we are in the regime where the network can store things for a long time, which is the regime where we usually want to be in applications involving long-term dependencies. Okay, so this is really important. The total gradient is the sum of terms, some of which will vanish and others will dominate exponentially. The short-term effects will dominate, the long-term effects will vanish. And so the network will tend to focus on the short-term effects and not be bothered too much with the long-term effects. At least, initially, when the network is training, it's going to initially focus on the short-term stuff. Eventually, when it gets the short-term stuff completely right, maybe some of those terms that used to be dominating could be smaller, and then it can focus on the longer-term stuff. But it might take a lot of time because those gradients become very, very small. Okay. Yeah, and this is really different from the kind of vanishing you have in deep nets. Although there's a connection, it's different for several reasons. But so one of them is that we have the same weights at every layer in the case of a recurrent net, and that means that the dynamics, the sequence of Jacobians tend to converge much faster to either explode or vanish. So think about it like this. If I'm going to multiply a bunch of numbers together and they're all the same, that's going to converge very fast to either 0 or infinity. But if I'm allowed to multiply like small, large, there's going to be some cancellation effects. So it's not going to converge as quickly to something bad. So that's one way to think about it. In high dimension, it's even more important, that effect, because you have different directions. And it might explode in some direction and vanish in other direction, and then one is going to really cancel the other. So that's really a different situation. Yeah, and also because in the recurrent case, also the total gradient on the weights, because they're shared weights, is this this sum over the different times, whereas in the non-shared case, like the normal feed-forward net, they all get their separate gradients, so they don't like hurt each other in that way. Okay, so to summarize, if the eigenvalues of those state-to-state Jacobians are greater than 1, or at least one of them is greater than 1, you can get gradient explosion. If they're less than 1, for sure you're going to get vanishing. And if they're random, well, the variance can grow exponentially fast. Now, how do we deal with this? So it turns out that there's a very simple trick to deal with a case where the exploding case. So first of all, the exploding case isn't that common in practice because we tend to want to remember stuff, and then usually that case the network won't necessarily go there. But if it does, by mishap during training, you can use what's called gradient clipping, which I'll explain later, where you just prevent the gradient from being too large when you update. And the one that's harder to deal with this is the vanishing case. So besides the gradient clipping trick, which is one line of code here, there are other tricks. So the gradient clipping trick is, there are different variants of it, but the simplest one is just prevent the norm of the update to be too large by taking the gradient and then thresholding its norm. So if the norm is greater than some threshold, make the norm equal to that threshold and then continue with that. Do the update with that. And we can also, actually see that this trick works in low-dimensional cases where we can visualize things. We find that in recurrent nets, the shape of the objective function isn't the typical valley that we think about in sort of optimization, continuous optimization problems. It's more like things like this, where you have these cliffs corresponding to these regions where you transition from one basin of attraction to the other, and where the derivatives could be very large. Yeah, well, I didn't explain why the derivatives can explode. So that's actually a cool thing. When you look at the basin of attraction story, so remember, we're going to have these regions where the derivative is small. Here the derivatives are going to be small, less than 1, and converging, and here as well. But in between, they have to be large. Because think about it, a small perturbation here can lend you either here or here, which is a huge effect. So that means the derivatives of those Jacobians here, they must have huge derivatives around here, right? Because a small change can make a big impact. So there are places in the state space where things are bad in the sense that the gradients will be large. And so we really need those clipping things. And this is kind of what's happening here. When you get close to this region, you have a huge derivative. So this is the cost with respect to parameters. And the clipping trick, what it's doing is that when you get close to this large derivative place, if you didn't clip, the gradient would be so large that the parameters would go crazy somewhere. By bounding them, you go away from that cliff, but you don't go too far, and then you can continue sort of going down this slope, which would it's like a dangerous place to be if you just trust the gradient. Another reason why we want to clip gradient is that we can't really trust large gradients. Remember that what's the gradient, right? The gradient is supposed to tell us if I make a small change of the parameters, this is about the change in the cost that I'm going to get. And when you have a large gradient, it's something crazy. It can't be large everywhere. So you can't trust that to make your step, because it's saying, oh, that I could have a huge reduction in the cost if only I made a small change in the parameters in that direction. Of course, it's not true. It's true only infinitesimally when it's like here, when you're sitting here, it's promising you that if you make a small step, you're gonna have huge drop, and it's gonna be true for a very small time, but then it's not true anymore. So basically you can't trust large gradients when you do gradient descent. Okay. It turns out that when we were studying this, we proposed something which is very close to the GRU that I'll tell you about later, which is a simpler version of the LSTM. What else? delays. So another trick to deal with long-term dependencies that was actually proposed, delays and hierarchies were proposed in the 90s, in addition to the LSTM, as a strategy to deal with long-term dependencies. And the thinking is very simple. If we can create shortcuts in the unfolded graph, the number of these Jacobians that we need to multiply, the number of these nonlinear time steps that are going to be composed can be made smaller, at least on some paths. So if I have delays like in the upper right, what's going on is, of course, there's some path that goes through all the time steps, but I have these skipping connections through time, which create these shortcuts through which the gradient can flow through longer sequences. And similarly, in the middle figure and more recent models we're using for dialogue, if you have a graph that has both long paths and short paths, at least the gradient can flow through some of the short paths. So here, the way we create short paths is you have different levels you have a deep recurrent net, and some neurons get updated less frequently or more slowly with more some kind of inertia, so that the derivatives can flow over longer time steps in the higher levels, and at least some information gets through, and maybe the places where you have more frequent updates will be able to capture the short-term dependencies, and the higher levels, which change less frequently, will capture the longer-term dependencies. So I think this is a good plan, and there's still a lot of research trying to make that plan work. More recently, we worked on something like this for dialogue, where you have two levels in the recurrent net, one that handles the words in an utterance, and the other one that updates after each utterance, after each sentence. And so this one can capture longer-term dependencies, and those ones can capture the sort of the within utterance dependencies. Okay, now the LSTM and GRU are part of a family of recurrent nets that use gating units. So gating units are really a magical thing that's everywhere in many architectures, neural net architectures, but especially those that deal with sequences. And so here we're going to be using the gating units to create the kind of hierarchy and shortcuts that I was talking about here, so that in some places, instead of updating, we're going to be copying, right? So if the state is not updated but is copied, then gradients will just flow through directly. So how do we get that? Well, we create a self loop, which is essentially going to be doing a copy or an additive copy. So we have some state, and we're going to say that state is equal to the previous value times a gate, which is hopefully going to be 1 very often, plus something. The plus here doesn't hurt us. It's okay. The point is that when you unfold this, there's a direct path when the gate is 1 through the past, and you can compute gradients to this. So let's say the gate here is always 1, then what's going to happen is that the state is going to be something like st is going to be st minus 1 plus xt, right? So that's a really simple thing. In practice, of course, we're going to have a gate here, and that gate is going to control whether we actually copy and add some new stuff, or we actually ignore the past. So this is the central element of the LSTM. It has other gates which are less important actually, which decide whether we want to kill off that thing or whether we want to use the output for the rest of the network. This is the output gate. But more recent work suggests that these gates are much less important. So the really important thing is that we have these gates, and you find that gate is in the GRU as well, which is sort of a lightweight version of the LSTM. There was a question?
Yeah. So why did you say eigenvalue slightly less than 1? Why not just 1? Like, why not just real copy?
Well, I mean, it's hard to get it to be exactly 1, right? So if it was always 1 like this, the problem is now well, you can see that this sort of limits the expressive power of what can be done. For example, sometimes you actually need to forget things. That's why they call this gate the forget gate. I mean, remember that a recurrent net is trying to summarize things. And so this particular recurrent net with a gate here can choose when is it a good time to clear the state and thus forget some bit of information about the past, and when we should just continue adding up stuff from the outside world. Is that answering your question, or you had something else in mind?
So if the gate is forgetting, I'm fine. But
Yeah, that's what it's doing here.
But when it's copying, that's just...
It's the same. It's the same. I mean, if the gate is 1, it's copying.
Yeah, so in this case,
If it's 0, it's forgetting.
I think his question was, why does it need to be slightly less than 1?
Ah, slightly less than 1. Well, okay, so there are practical questions here. So, I mean, of course, G is not going to be either 0 or 1. It's going to be the output of a sigmoid that's going to be between 0 and 1, so it's not going to be exactly 1. And I guess that we'd like to have something that would be 1 exactly, but it's hard to learn something like this because we're looking for continuous quantities. And if we're going to be erring, we want to err on the side of contractive, so less than 1. And that's the strategy that's being adopted in these nets. I'm not saying it's the only way of doing it, but it makes a lot of sense.
Okay, so roughly, ideally, it could be 1.
So actually, that's right. So we had a paper a couple of years ago called unitary recurrent nets, where we try to make it exactly 1 in a complex domain. And it kind of works, but it's missing the forgetting part. And so we're trying to, put in some forgetting in other ways. But yeah, you could force it to be 1, but in the real case, it's sort of a bit drastic. You only get an addition, for example. Remember, look, one interesting thing about this is that if you have exactly 1 in this formula, you're just adding things up. So it's accumulating, and so it doesn't care about the order in which things were presented, for example. So there are issues, but I think there's still a lot to be understood about these architectures, and it's still pretty much a field of investigation how to design those architectures. Let me tell you a few words about another way that you can use gating mechanisms to sort of copy the state in a way that you can now remember things from the very far past. And this is something you find in neural Turing machine, to some extent in memory networks, that were introduced about 3 years ago. And that use a gating mechanism which has come to be known as a soft attention. So the idea of soft attention is that we're going to use a gating mechanism to decide on which parts of the state or the input we're going to be focusing most. So we're going to actually take a linear combination of, say, the content of a set of cells. So we're going to have a set of cells that have, say, a content Ci at time t. And we're going to form now these gating things. So this is a vector. This is a scalar. And now for each I, each position in my memory, we have all these vectors at each position in the memory. We're going to decide whether we actually read something from this, and we can also write there, or not. So if the gate is 0, then we don't care about what's going on. If it's 1, then we do. And if we make those g's sum to 1, then, which is the typical way we're doing this with a softmax, then we're just going to have a soft selection of one position and maybe other competing positions. And we're going to take the content of these and use them for the next operation. So now we can read from a memory with a sort of soft pointer that decides where to look. And so why is that interesting? And of course, you can do the same thing to write by doing an update at each position proportional to those gatings. But I'm not going to write the math for that. the interesting, so I'm going to just show that in a picture. So what is this picture supposed to be? This is the state of my memory, which is now a bank of these vectors at each time step. And remember, a good way to understand what's going on in recurrent nets is to think about the unfolded graph of computations. So that's what I'm doing here. I'm thinking about the sequence of states. Now the state is a complicated thing. Oh, another meeting? Oh yeah, I'm supposed to do a movie. So this sequence of states now is partitioned into all of these vectors, and we're going to have this attention mechanism to decide where to read and where to write in a soft way. So it's really reading and writing at multiple places at the same time. But for the sake of mental visualization, we can think of it like this. There'll be some memory cells where we're neither writing nor reading, and so the content is just going to be copied. And that means that gradients are going to flow through this directly without any, in that case, the Jacobian is exactly 1 when you're just ignoring those cells. Sometimes the content of a cell is going to be obtained by some transformation of the content of another cell. So we're going to writing in some cells, and we're going to be reading in some cells to write in other cells, or updating some cells. And so there's going to be some complicated graph of these readings and writings. So now you see what's going on. We can store something in this memory, and until we overwrite it, it's going to just be copied. And so information can stay there and have an influence over a very long time span. So this is something really important that I think we're only starting to realize the potential of in terms of the designing systems with very long-term dependencies. So as I mentioned, the attention mechanism itself, there's a long history of earlier work, but there's a particular variant of it using a soft attention that's called a content-based and address-based attention, which has really worked out well, especially in the machine translation applications. So imagine that we are reading this sequence of words in French, and we're going to be translating. That means we're going to be generating a sequence of words in English, and we've mapped the words into feature vectors, say using a bidirectional recurrent net. So now at each position in the French sentence, we have a vector that tells us about the meaning in that area, maybe the meaning of that word in its context. And we have this other recurrent net, which is going to generate one word in English at a time. And when it generates the next word in English, would like to use an attention mechanism so that instead of looking at the whole sequence as an aggregate, the whole French sequence as an aggregate, it's going to pay attention to one or a few places in the input. So if you think about it, when you're translating, of course it's not word to word, but it's approximately word to word, right? So there's like going to be one word or a couple of words that are really going to be dominating the meaning of the new word that we're going to be generating for the translated sentence. And so very often in applications you see this, that in order to produce the next bit of information, we are really focusing on a few bits of information from the context or the source or the input. And in the case of translation, it's very obvious that this makes a lot of sense. What happened, so this interesting historical story here, we had a paper and we were working with this sequence-to-sequence, which we call the encoder-decoder architecture for mapping a sequence, say in French, to a sequence in English. But the problem with that was that, remember the architecture I showed you before, you read the whole sequence, and now you have this vector which is supposed to summarize everything, say from the French sentence, and now you're going to use that to condition the generation of the English sentence. That works if the sequence is short, like 10 words, 20 words. But when it gets above 20 or 30 words, it's really hard to train those recurrent nets to remember that much stuff in detail. It tends to drop off the details. Because the summary, is sort of a summary, so it doesn't, it loses details. But, so try to think of doing machine translation this way, translating a whole book. Let's say I'm going to read I'm going to read the deep learning book in English, and then have it all in my head, and then write the French version. Does it make any sense? No. So that's what we're trying to do here. Whereas if you use attention, you're going to say, oh, I'm going to have 2 pointers. I'm going to have a pointer to the French version that I'm creating, and I'm moving one sentence at a time, and so on. And I have a pointer to the English version, keeping track of where I'm in the English version. And mostly the English version is going to move, one step at a time. Sometimes we need to look back a little bit, but mostly those 2 pointers track each other. So having these 2 pointers is really the key, and that's what attention gives us. So it's a very powerful mechanism. So thanks to this, we were able to reach the state of the art in machine translation around 2014, 2015. And thanks to this and a bunch of other tricks, Google just a few months ago released their neural machine translation system, which you can now use with Google Translate, at least for a number of sentence pairs, that has really amazing performances. These numbers are a bit confusing, but the summary is the following. I'm going to use the whiteboard again. So they have evaluated the machine translation, the neural machine translation systems, and compared it with the traditional n-gram-based machine translation by asking humans to rate translations. And so this is sort of the quality of the translations according to humans. And on that scale, let's say this would be the quality of the translations reached by humans. So that would be, you can see that's the column human, so it's like about 5 or something. And there is the quality of the translations that used to be done by the traditional system, which would be, say, around 2 or 3. And there's the quality of the translations that are done by, this was the old stuff, and that's the new stuff, okay? So whatever, something between 4 and 5, right? Say 4.5. So it's a huge advance, and you can feel it if you were used to doing machine translation using Google Translate, using some of these language pairs, and you try them now, you'll see the difference. I mean, it's much better. Okay, so this idea of attention is used in many other settings. One example is the pointer network that came out just after this machine translation thing by Oriol Vignal. And we've been using this also in translation. So there's a problem in translation where sometimes in the input sequence we have words that are proper nouns or names of rare words or things like this, names of places, and they might not be in your vocabulary. So this sort of created a bit of a problem, but it can easily be solved using a special kind of pointer and attention mechanism. And the idea is that at each time step, instead of doing the normal softmax over all the words in my vocabulary, I sort of extend my vocabulary to include all the words that are in the input. And the way I can do that is I can say, okay, so I have the choice when I do my softmax to either pick one of the words in the vocabulary, and I'm going to compute a probability for each of them, or to pick a word in the input. And then the way that I'm going to choose the word in the input is I'm going to compute a score for each word in the input. I'm going to compute, for each position now, I'm going to decide whether it's the right place to pick the answer for the next word. So, between French and English, it works really well. We just copy a word in input into the output at the right time. But you could do more complicated processing. So let's say you're translating from English to some other alphabet, say Hindu. You need to translate the letters into a new alphabet. And so you can do that by inserting some special network that learns to do this. It's called transliteration. Right, but the important thing here is that, again, this attention mechanism can allow us to do things that are really, really practical in many applications. You can play games, other games with the architecture and try to also understand theoretically what those mean. So we've talked about skip connections. We've talked about feed-forward connections, and we talked about how we care about the length of paths. One interesting question is, what kind of architecture would give rise to what kinds of lengths of paths? There's sort of two effects that we may be looking for. One effect is we want short paths to be present because we want gradients to be able to propagate more easily. But if we have a deeper network, in other words, a deep recurrent net with multiple layers, that's also advantageous because now we have these feed-forward paths that allow us to compute sort of more complex results. But if we have connections like this, and then connections back from top to bottom versus bottom to top, actually the impact is different in terms of the lengths of the shortest path and the longest path. And so we did experiments where we compare the two kinds of architectures, bottom up versus top down, and we find that one really works better than the other. And the reason is that in one case, we can actually have much longer paths, which sometimes is something desirable, than in the other case. So when you have the top down, you can actually have a fairly long path that goes, from the previous time step up, up, down, up, down, up, down, and so on. So it's actually worth thinking about sometimes the details of the architecture. I mentioned the unitary recurrent nets. You can play games with the architecture in various ways, like force those matrices to be orthogonal or to be unitary. You can also create skip connections that are random. So instead of having these fixed skip connections, you can have various kinds of skip connections that are stochastically, decided. A little bit like in dropout, but here you have the connection or you don't. You can also inject in the recurrent net architecture kinds of things that we haven't talked about yet in the summer school, but latent variables. So the recurrent nets don't really have to be deterministic. Up to now, I've talked about everything being deterministic, but some of those nodes could be stochastic as well. And the language of variational autoencoders and variational methods could be applied to training those kinds of recurrent nets with latent variables. So a few years ago, we had this variational generative recurrent nets, and there's been a lot of these kinds of variations in the literature since then. You can, for example, we've used them in dialogue to inject random choices at the high level of the hierarchy. I'm not going to explain the details here because we haven't talked yet about generative models. Okay, let me now talk about a few related architectures. So remember, I started the discussion by talking about the decomposition of the joint into a conditional as sort of one of the hallmarks of the probabilistic interpretation of recurrent nets. But actually, this has been around in other settings than recurrent nets and other kinds of neural nets. In fact, first with sort of linear models. This was in Brendan Frey's thesis in 1997. You have the picture on the right-hand side where we decompose the joint into a product of conditionals, but here there's no sequence. It's just a tuple of random variables, and we're going to have, say, a logistic regression of the ith variable or the tth variable given the previous ones. And in this way, we can represent the joint distribution of a tuple of binary variables. or we can generalize that to any kind of other random variables for which we can have a parametric distribution, and we're going to make the parameters of that distribution be computed by our network at each point in that sequence. So one way to visualize this is here, where we're going to have sort of just a unit without input that's like a bias unit, which computes the probability of the first random variable. And then we're going to have a very simple network which predicts the second one given the first one. And then another network which computes the third one given the first two ones, and so on. Right? So now we're going to have this sort of n squared matrix, which with some of the connections being left off, so that only the past can be used to predict the future in this arbitrary ordering. Because now we're not talking about a sequence, we just have a bunch of bits or a bunch of numbers, but we choose an ordering, and then based on an ordering, we say we're going to predict the conditional probability of the ith one given I to 1 to I minus 1, right? The previous ones. In NIPS 99, my brother and I had a paper where we extended this idea to neural nets. So now, instead of having these linear models, we have a sort of MLP, one hidden layer MLP, but with a special structure in the architecture, so that the hidden units, so that the overall graph maintains this constraint that the ith output only depends on the inputs from 1 to I minus 1. And we can do it in various ways, but one way is that we have these groups of hidden units which only take inputs up to the ith input, and then connect to I plus 1 or more. So that was actually our first foray into thinking about neural nets as a way to deal with the curse of dimensionality in trying to model joint distributions. And more recently, Hugo, whom you heard yesterday, presented in 2011 a variant of this, by the way, which we call autoregressive, neural autoregressive models, which he called the NADE, neural autoregressive density estimator, in which there's a particular parameterization which allows us to compute these probabilities much more efficiently. I'm not going to go into the details. And it works quite well in terms of a density estimator. It can be generalized to variables that, of course, are not just binary, but any discrete, but also continuous. There's a lot of variations of this idea. More recently, this kind of models, these kinds of autoregressive models, have been incredibly successful as generative models of images and speech. And so you can have things like pixel RNNs, which use this kind of RNN architecture, but to generate the ith pixel given the previous ones. There are also versions that have a finite context, which are convolutional, and these actually give rise to pretty nice image generation, kind of state-of-the-art image generation. Okay, so this is my last slide. One of the open problems that I find really mind-boggling is how would the brain do anything like backprop through time? How would the brain, what's the learning algorithm in the brain that allows us to learn about sequences? And the reason I find this mind-boggling is that it doesn't seem very plausible that the brain would use a strategy anything like backprop through time. So backprop through time is this, we just unfold the graph, and we wait to the end, and then we compute the gradients as usual with the chain rule and backprop, right? What's the problem with that? The problem with that is that it requires us to store in memory the whole sequence, hold it there, look at the outcome, and then compute gradients in the reverse time direction. But it doesn't feel like that's what's going on in our brain. Like, we don't redo our life 1,000 times to see how we could have done it better, right? So maybe you would say, oh, we don't learn long-term dependencies, that's the length of our life. Maybe we do it on a day basis, maybe. And so maybe like each night we replay backwards the things that we've done during the day. That's possible, but it doesn't feel really right. So maybe there's something else. So let me say a few words about another strategy to compute the gradient, which was introduced in the late 80s called real-time recurrent learning, RTRL. But what it is, for people who know about various forms of gradient computation, is just the forward mode, the forward evaluation of the gradient. So in other words, as we are moving forward in time, we can compute the derivative of each of the state variable with respect to each of the parameters. And each time we get a costs, we can use that immediately to make an update. So we can do online learning. We don't need to wait for the end of the sequence. So this looks very cool, right? It's the kind of thing we think the brain might be doing because we do online learning. Something happens and I don't know about you, but like something bad happens to me and I somehow immediately try to associate with the things I might have done wrong in the past. So it sounds like something that could be done by the brain. Unfortunately, if you take the equations for this to the letter, you end up with computations that are not practical, that are not exponential but polynomial in a fairly bad way that wouldn't scale with something like the size of the brain or even the size of the kinds of networks we're trying to train for things like speech and language. So this is still an open question. Like, how do we do something like an online update that's computationally efficient? So there is some work already in that direction. I don't think it really solves the problem yet, but I think it maybe indicates a good direction, where instead of trying to do an exact gradient computation, maybe there exists some approximate gradient estimators that statistically might be unbiased, or even if they're a bit biased, maybe that's okay, and would give us these kinds of online estimators. So this is still an open problem, of course. All right, so now I'm going to take questions. Yes?
General question, do you have any information in terms of when is bidirectional RNN more superior than forward RNN, or is it?
Well, anytime you can do bidirectional versus single normal RNN, do bidirectional. Because you just get more information. So sometimes you can't because, like in the case of when you're generating an output sequence, you can't be bidirectional because you're not supposed to look at the future that you haven't generated yet. It doesn't make any sense. So it has to go left to right or right to left, but you can't do both, or at least not in one pass. So there are many places where you can replace a normal recurrent net, or LSTM, GRU, whatever, by a bidirectional version of that.
From my personal experience, I find that sometimes using bidirectional doesn't really help with performance, actually increase the training time.
That could be. So it's going to depend on whether there is a good solution to the problem that's only causal, looking only at the past, or actually it's useful to look into the future. Yeah?
And when using bidirectional networks, so at the end you get two vector representation of the states.
Yeah. Yeah, you just concatenate them, or you can take the concatenated into some further processing like an MLP or whatever.
Adding them up, you lose information, right?
No, yeah, we don't add them up, we concatenate them. Exactly. Yeah?
If the RNN is really encoding the chain rule, why do you need bidirectional?
No, the RNN is not encoding the chain rule. It's trained using gradients computed by the chain rule. The backwards.
Yeah, the probabilistic chain rule.
Oh, the probabilistic chain rule. Yeah, that's what I'm saying. You can't use the bidirectional RNN when you're computing the probabilistic chain rule.
But what I mean, when you say that the RNN is, the simple RNN is doing the probabilistic chain rule,
Yes.
then you don't need to care about encoding the time.
No, you don't need, you don't need and you can't. It doesn't make any sense, right? But that's when you're producing an output. But when you're reading an input or anything you're reading, you could process that as much as you want in any direction in any way you want. That's all, free game. Yes, in this side. Yes, please.
So in the beginning we talked a lot about how we can make probabilistic models of sequences.
Yes.
And then we spent a lot of time talking about RNNs
Well, they're deterministic in their state, but the output is a random variable that we can compute the probability and sample from.
Are there theoretical advantages?
Sorry, I didn't hear well.
Are there theoretically proven advantages to doing like these variational inference schemes within the RNN?
So the question is, are there theoretically proven advantages of these variational schemes for RNNs? Well, we don't need those variational schemes for the output side. So, the things I've talked about in the beginning, we don't need anything fancy here. We can directly compute the probabilities, the likelihoods, because these are not latent variables, they're observed. So everything is easy, simple, no need for variational anything. Where the variational tricks come in is if we want some of the latent variables, some of the hidden units to be latent variables. If we want to have latent things inside, then, well, one approach is to have different parts of the RNN compute posterior distributions for these. So that's like what we call the encoder part, like in the variational autoencoder. And then the rest of the RNN, which uses those things, is like a decoder, if you think about the variational autoencoder. There's no guarantee that this is going to bias anything, but the intuition is that we would like some of the randomness, when you think about the RNN as a generative model, like all the autoregressive models, the places where it injects randomness is the input space, is the data space. And one of the motivations for deep generative models is that we'd like to think that a better way of generating, instead of directly painting the pixels one after the other, is to first think of, what is it I want to draw? What are the main objects? What are the colors? Where are they located? And then sort of put all these details after I've decided the big picture. So we first generate the high-level things, and then condition on that, we generate lower-level things, and so on and so on. So there we need latent variables if we want to go this route. There's no guarantee that this is better, but intuitively it makes a lot of sense. And this is what has been motivating a lot of the deep generative models, including the recurrent nets with latent variables. Yes, in the back there. I don't hear you well, sorry.
There's a paper from your group called Traditional Propagation.
Yes.
It is proposed as an alternative to bad propagation, which is more biologically plausible.
Right.
So I'm wondering if it's something related to this slide.
Unfortunately, no. This slide is about temporal dependencies. And the equilibrium propagation is about a different kind of recurrent nets, which I haven't talked about, which is the kind of recurrent net you'd use to handle recursive computation for a given input. So the kinds of recurrent nets I've been talking about here are recurrent nets that handle a sequence, whereas there's another kind of recurrent net, which is also something we have in our brain, which is that given like a current image, our brain is a dynamical system that will sort of evolve over time with the input fixed. There's going to be some dynamics running. And in the case of the equilibrium propagation, we actually let those dynamics converge to a fixed point. So these kinds of networks, recurrent nets, they're called fixed point recurrent nets or whatever. This is sort of an orthogonal question. So you have the dynamics given a particular input, and then you have dynamics over time with the time of the data. So these are like two different things. And equilibrium propagation is really looking at the dynamics within one time step. In the case of the feed-forward computation that we usually have, there is no dynamics. It's just bang, 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 we get the output. But the brain has these feedback connections, and so it's not just bang, 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 we get the output. Actually, you get that, and then things evolve to maybe a better configuration, which you can think of as a better interpretation for the current input. Yes, maybe this is going to be the last question.
So we talked about vanishing gradients.
We talked about what?
Vanishing gradient.
Vanishing gradient.
And in feed-forward networks, the state-of-the-art resonance use skip connections.
Yes. So ResNets use skip connections. It's a very, I think it's probably inspired by the things that have been done with recurrent nets. Yes.
So has any architecture been proposed to utilize skip connections for recurrent networks to avoid vanishing breaking problems? Or
I think you missed the slide.
I think so.
Yeah. Well, I had one example here. No, that's not it. Sorry, wrong picture. But anyways, yes. This was proposed in 1995, or even before, to have, I think there's even a paper in 1994 to use the skip connections through time as a way to deal with the long-term dependencies issue. And it's, it doesn't completely fix it, but clearly it helps. So this idea is really old, and it's these kinds of ideas in recurrent nets has probably influenced the ResNets, if any. I mean, all right. So thank you very much, and I guess we can have our break now.